In the last episode, I showed the design of a 4-input multiplexer to control the flow of data onto the internal data bus. Stay tuned, as today we're going to build a test circuit and see if we can't move data between the registers inside the CPU. Have you ever wondered how you can make your own CPU or microcontroller? Have you ever been curious about field programmable gate arrays, also known as FPGAs, but find them to be mysterious black boxes? Or wished you had a microcontroller-like device with a larger memory address or wider data bus? Well, stay tuned as we delve into the world of FPGAs and create a CPU and eventual microcontroller from scratch. Hello and welcome to 100 Random Tasks. I'm your host, Philip Lett, and if you like what you see here, please give us a like and leave a comment. And subscribe if you want to be notified when more videos are uploaded, and it would really help the channel. With that, let's get started. If you remember from last time, I had placed an input buffer and a tri-state output buffer connected to the data bus. It turns out that this doesn't synthesize correctly and throws an error. After some Googling, I wasn't able to easily find a correct Verilog version for the I/O buffer. Instead, I added a new schematic file and used the IOBuff primitive that is part of the software. I created a new file because the primitive is only a single bit and we need 8 bits. So to keep the design uncluttered, I used a new schematic symbol block for the top level schematic. It's necessary to use bus taps with this, which is one of the tools in the schematic capture toolbar, in order to make the buses work correctly, and you just have to name each wire with the bit position that tap represents. I won't go through the making of this block. By now you should have a feel for how to do it, and I'll leave it to you to finish. Leave a comment if you would like me to describe this further. Once this was done, I generated the schematic symbol for it and added it to the top level. The data out flows data from the CPU to the data bus, and the data in flows data into the CPU. That direction is controlled by the OE pin. You'll notice that I've added an inverter to that pin. This is because it is active low, meaning data will flow out of the CPU when low. But as we'll see later, the 74HC245 transceiver is also active low, so we don't want both to be active at the same time. This ensures that when the I/O buffer is active, the transceiver is inactive. I've also added all of the I/O markers for the control lines, so they can be routed outside of the FPGA. And I temporarily connected the accumulator to the data bus for this demonstration. Next time, this will be connected to the arithmetic logic unit, or ALU for short. Looking at the test schematic, it has the 4 lower bits of the address bus A0 to A3 connected to LEDs, which watch the output from the address register. I'm only using the lower 4 bits to keep things easier to see for now. The clock will be connected to the astable monostable clock that I have on the development board. A simple RC reset circuit with a push button, the 5 load and increment lines, which will just be a wire plugged into either 3.3 volts or ground, as well as the 2 select lines that control the multiplexer. And lastly, there are 4 LEDs connected to the data bus to monitor its state, as well as 4 dip switches buffered through a 74HC245 transceiver. Since the transceiver only puts data onto the bus, the direction pin is tied low. To control the data flow in the data bus, the memory output enable is tied to the enable pin of the 245, which will be controlled by another wire just like the control lines. So when the read-write line is high, whatever is on the internal data bus will be shown on the LEDs. And when it is low, the value of the dip switches will be placed on the memory bus and shown on the LEDs. With that out of the way, let's wire it up. I just noticed that I had an error on the schematic. Pin 1 of the 245 should be tied high and not low like I had originally. I've programmed the Spartan, and you can check out previous videos in this series to see more of that process. I've also added the labels for each of the control lines. Right now all the control lines are low. The select lines are 0, 0, so this points to the accumulator, and the read-write line is high, putting what's on the accumulator onto the memory bus and disabling the 245 buffer. If I switch it to read, it shows 1001, which is what the dip switches are set to. If I flip one of the switches, you see the value change. Setting it back to write and going through the select lines, all the registers are 0. Accumulator, data register, program counter, and memory bus. So let's see if we can't set the address register. Looking at the outline again, to load data from the memory bus onto the address register, we have to set the AR load pin. Set the select lines to 11 to select the external memory bus, and set the read-write line to read, which enables the 245 buffer and puts data onto the bus. So let's do that. First I'll set the read-write to read, and it has a value of 1001. I'll set the AR load pin high, and set the select lines to 11 to select external memory. Now I'll cycle the clock, and the value on the memory bus should pass to the address bus. Now the address register holds the same value. So what's going on here? Using the outline and redrawing the output section with the I/O buffer, you can see how the data will move around. Setting the read-write line to low, it takes data from the data bus and funnels it to the MUX, input number 3. If we set the select lines to 11, then that data is sent to the internal data bus and is accessible by all the registers. Then by setting the AR load high and cycling the clock, the value on the internal data bus is loaded into the address register, which is then sent out to the address bus. In this way, it's possible to load more than one register simply by setting the appropriate load pins. Suppose we want to send what's on the data register to the external data bus. First, by setting the select lines to 01, it funnels the data register through the multiplexer and onto the internal data bus. Then by setting the read-write line high, the internal data bus is sent out to the external data bus. If I set the AR output enable line high, the LEDs turn off, as this puts the address bus into high impedance. This will allow other devices to access the memory bus if needed. We know that works, so I'll leave it set low for now. Let's have a look at the program counter. I'll set the AR load back to 0 and set the select lines to 10, which is the MUX address for the program counter, and the read-write to write. Now it shows 0, but if I set the PC increment line high and cycle the clock, it should start counting. Perfect. Now let's put the program counter into the data register. For that, I'll set the PC increment back to 0, the DR load to high, and cycle the clock. If it loaded correctly, then by setting the select lines to 0, 1, the same value should be shown on the LEDs. Perfect. Next I'll load the accumulator with 1100. To do that, I'll set the select lines to 11 to access the external bus, set the DR load to DR load to 0, and the accumulator load to 1. The read-write to 0, and set the dip switches to 1100. And cycle the clock. I'll increment the program counter value now to 0110. And with that, let's go back now and check the values of the registers. The accumulator should have 1100. Good. The data register should have 1010. Good. The program counter should have 0110. Excellent. And the address register still has 1001. Lastly, let's pass each register value to the address register. I'll set the read-write to 0 and set the dip switches to 0. Set the AR load and all others to 0. The select lines being 0, 0, select the accumulator. Now we'll cycle the clock. Good. Shows 1100. Data register. 0101. Program counter. 0110. And finally memory bus. All zeros. Excellent. And that's it for this part. So far the CPU is functioning as expected, and we've been able to move data between registers as well as external memory. Next time we'll add some computational power to our simple CPU as we design the Arithmetic Logic Unit, or ALU. It will only have a few functions to start, but will be easily expandable to add new functions later on. So make sure you subscribe so you don't miss it. And if you've made it this far into the video, thanks for watching. See you next time.